So, welcome everyone to the first EDS seminar of this year. The title of today's seminar is VLSI Design Automation and Computational Resiliency and Security. We are very happy to have with us Dr. Riadul Islam as today's speaker. So let me just briefly introduce our speaker today. Dr. Riadul Islam is currently an assistant professor in the Department of Computer Science and Electrical Engineering at the University of Maryland in Baltimore County, USA. He did his Ph.D. from the University of California and Santa Cruz, and where he published his papers on flip-flop registers that resulted in the first ever one-to-many current port clock distribution networks for high-performance microprocessors. Before joining the University of Maryland, he was an assistant professor at the University of Michigan at Dearborn, Michigan, USA. He is a senior member of IEEE and a member of ACM and IEEE Circuits and Systems Society, VSA Systems and Application, and a member of the Technical Committee of VSA. And also IEEE Circuit and Automation Society and IEEE Solid-State Circuits Society. He has 2 US patents and several publications in top journals like IEEE, ACM, NSF and Nature. His current research interests include digital and digital CMOS circuits and their applications. He is an associate editor of the Sprinter Circuit Systems and Signal Processing Journal and the editor of Frontiers in Communication and Networks Journal. So he is a recipient of 2021 National Science Foundation or NSF ERI Research Investigator Award 2021 and also the Maryland Industrial Partners Award and Maryland Innovation Award. Okay, so I hope you are going to enjoy this talk today. Please feel free to ask as many questions as you can. তোমরা বাংলাতেও প্রশ্ন করতে পারো, কোনো সমস্যা নাই. Ask him about his field of expertise. You can also ask him about PhD admissions, funding, and anything related to scholarships in the US universities. Okay. So with that, I would like to invite our speaker to deliver his talk. Thank you.
Thank you, Dr. Mainu. And I must thank Dr. Hassan for inviting me and giving me the opportunity to come and talk with you guys. So I will start, and since I have a very restricted time bound, I believe, so they have a faculty meeting coming up. So the outline of talk is I will talk about the basic concept of RDL to GDS2 generation, the basic way we design our microprocessors, and then I will give some state-of-the-art or industry issues related to manufacturing. Then I will talk about some of my research in machine learning application in EDA, electronic design automation, and I will go away from it a little bit because I am doing some research on cyber-physical system resiliency and low-power IC design, and some research again away from my core research of VLSI. It is vehicular network security. So let's jump into RDL to GDS generation. This is the standard way the industry design our microprocessor. So the first step is we'll have our design in high-level language. You can write it in any kind of HDL, system verilog, or VHDL. And after that, basically we need some constant file and some specifically technology file that requires to understand, the tool has to understand what I tell in my high-level language description. So I have to define my problem, I have to tell the tool that, okay, I want to design this. Then the logic synthesis will come into effect. Industry uses 2 tools. One is from Cadence, which is Genus, and Synopsys uses Design Compiler. So you give all those information into logic synthesis tool, it will give you a netlist. which is nothing but a very simple gate level netlist. So after we have this gate level netlist, it goes to our base and output. So Cadence has Innovus, and then Synopsys has ICC2 currently. So these are standard industry standard tools. Then what happened in place and output? We go through some specific steps, something called partitioning by design, floor planning. Then we go to our block tree synthesis. After that, we went to our primarily the routing phase, which is the hardest process for the tool. Routing means I will put together my millions of gates. Now the tool has to understand how I can route my signal from one point to another point. So this is the hardest part for my tool. That tool basically will do in two steps. One is global routing, so that will estimate whether my design is routable or not. So once it estimates that okay it is routable, then it goes through detailed routing phase. So it will then connect all the modules together, one to another. And this takes long time in general. After that, in general, we do the sign off and we generate our GDS2 file. So in general, these steps I talked about, it takes about 7 to 10 days for a gate size of about 10 million logic gates. But this 10 million logic gate is about 50 to 100 million of my transistor out of my, let's say, 5 billion or 5 billion transistor processor. So it is a part of my processor only, and it takes about 7 to 10 days. So as you could see, this is the engineering cost, right? So you guys are engineers or will be an engineer. Now you are doing it as an Intel lab or any company, but it will take long time, right? So this is a problem there. Now, even that this is not a whole story. I'll tell some of the issues with these steps we have, standard steps. After all this process, the things will break because you'll find out, like, I don't know, if there are senior students, you know probably the Cadence. So when you do some sort of layout, and after that layout we see some VLSI violations, then in general we go manually and fix those issues, right? So these tools will also face those issues end of all the process. This 7 10 days. So you see all those issues, the engineer has to go and fix those issues and run this 10 days process again. So this is a real problem. So what are the issues in general we have in our manufacturing? So lithography, I believe if you have taken any class, Dr. Maynu will know more than me. So it's a lithography is a standard process, the way in general we print our circuit, right? So in microfabrication, we have this photoresistive chemical process where we have this photomask, and through that basically we print our circuits on substrate. Now this curve, as you could see, is saturating at certain point. So this technology scaling is not smooth from the industrial perspective. So this is one of the issues, and the primary source of these issues, you could say that edge placement error, EPE. And for this in general, this smoothness of your printing are not correct. Like as you could see, we expect a rectangular shape here, but it is not smooth. So some of the issues are alignment, critical dimension, uniformity, and lines are not fair. So those are the real issues industries are facing. As a result, as you could see, the design rule count increases over the years and over the technology nodes. And this also translates into the amount of mask we need for the fabrication, as you could see. And these are the issues we face, and end of the day, the cost of our chip, which is supposed to go down, is increasing now. Now, as you could see, about 14% cost of the chip is increasing nowadays. And it is up to 7 nanometer, right? Now we are in the era of 3 nanometer and going down. So bottom line is, the reason I am showing this, I want to tell you guys that the fabrication process is hard and time consuming, and the price of the chip is increasing. So if the price of the chip increases, what happens? The mobile phone you guys are buying, or the processor we are buying, it will increase, right? Which you don't like as a consumer. Now, all those issues are there, That is the reason that my research motivation is there, because I wanted to merge my research with the industry, create value in my lab. So what I did, first of all, I will give you the basic definition. Anybody know what is machine learning? Can you define?
Actually, machine learning
Okay, very good. Sit down, please. So I don't want to put anybody in the spot. The machine learning is for me, it is a basic algorithm, which I define as a PTE. So there is a process, and there is a task associated with my process, a performance P, and the task associated with that T. So how do I improve my performance? Basically, over the time, I want to train myself. This is how our brain also works. So if I train my brain over the time for certain things, it learns, and I become more smarter. Or I could say, we build our network in our brain. So if you give me a task, basically I want to feed that task into my brain network. So any problem associated with task next time coming, I will quickly feed in my learn network, and then I can answer the problem or solve the problem. So this is the basic learning. Basically, this algorithm in general we define. So type of learning, it is kind of a tutorial for me, so I'm just going over very quickly. So there are few types of machine learning. Some called supervised learning, where we give a features of my data, also give the output. So the label will be there. This is called supervised learning. And there are also unsupervised learning, where we only give the features of my data. We don't need the outcome. Basically, it will learn and give you the output. And semi-supervised also there, where self-learning or some sort of where the part of the data will be labeled and part of the data will not be labeled. I am not going into detail of those, but these are the basic definition. And another type of machine learning is reinforcement learning, where for certain actions we get some reward. So machine learning, like the problem in general we solve is like classification, where we said, okay, this problem is 0 or 1, binary decision, where we classify things. Or it could be multi-class also. There could be like MNIST data set is some sort of machine learning classification, where we classify 10 digits, right, 0 to 9. So there are about 2 will be 10 classes. Or this could be a regression problem, where it is a continuous output. Some sort of, let's say, if you want to get a home at some location in Dhaka city for certain features, or the features could be number of bedrooms and the size of your home, then it could predict the price over the years. Then we could have dimension reduction problem, and we could have structure prediction and also anomaly detection, which is also part of my research. So ML, like how the ML is helping our EDA domain, right, electronic design automation. So what we do, we could improve the yield. We could also lithography hotspot we could detect, and data path irregularity, also the timing violations. Yes.
What is lithography hotspot?
Lithographic hotspot means like the issues you'll find for lithography, you need certain pattern, right? So the machine learning could identify that if I have that kind of pattern, the issues will be there. So then you have to improve that like your layout in a way that lithography hotspot will be not there.
But you need a lot of data set, right?
Yes. So this is the biggest problem in EDA.
So it will be kind of like image classification, right?
Image, like lithography way, it is image classification. But I will give you example. It is not an image classification problem. So for me personally, I spent 1 year to collect data. And the problem is like nobody will give you data because these are all confidential. The reason is it is associated with the technology node, and the company will not allow you to publish those. Right? So those you have to basically, I have to sit there and implement hundreds of design and collect data. I'll tell you how I did that. So the way I did that is basically, if I have a layout, virtually I can create some sort of grid from my layout, right? So just let's say I said 24 metal 2 layers is my grid. So then I will go each location of those grid, right? I can go each location from in my layout and collect features from those locations. The locations could be anything but, let's say, my standard cell count, number of standard cell inside this grid. number of pins inside this grid, number of metal layer inside this grid. So these kind of features I can collect. And after that, what I did in general, I'll tell you what I did, but this is the way we collect features. As I said, these are the stuff you cannot find it in websites, right? So those data sets will be not available ever. So you have to basically make your hand dirty and put months of work there. So for me it was like more than 1 year to collect. Yes.
Sir, what design tool did you follow? We can add this to yours.
So I designed hundreds of things, like let's say communication unit, a processor, different kind of processor, and DSP units, memory units. So any kind of design you have, you could collect data, and you want diversity in your data set.
Sir, what design rules did you follow, like GPDK 45 or industrial?
You are asking technology node.
Yes,
right?
yes,
Yeah.
yes.
So technology node for me, it was initially I used 32 nanometer from CMOS. The standard one they give for the education free, and then I got 14 nanometer from them also. So I have data set like more than 100,000 data from two technology nodes. One is 28 nanometer, which is 32 also, and 14 nanometer. So this research is valuable in terms of the reason is like the industry is working continuously. This paper was published by Google in 2021 in Nature. So basically what they wanted to show how we can optimize the placements. So think about it, in your processor there are a few millions of gates, right? So these millions of gates has to place in your chip in certain constant, right? Area constant. So how are you going to do that? So what they did basically, they collected features like netlist, metadata from netlist. Netlist, it could be individual gates, their connectivity, and from there they built a graph neural network. Basically they embedded the graph. After that they sent it to a fully connected network, and basically finally they got a netlist of metadata embedded. And they applied a reinforcement learning algorithm here, which is used force directive method. Anybody know what is force directive method? Basically it is a spring law, right? Think about a spring, it is connected to two nodes. Now if I set my law, the force between two nodes will be proportional to the distance square, right? This is the spring law. So basically this method sees like which modules are talking to each other more time, right? They are connected strongly, so you could place them together. Okay, so they applied this RM method, and the cost basically reward was 𝗔𝗂𝗃𝗃, half perimeter wire length, and congestion. So I'll give you one example. Yes.
স্যার আমরা যে ডেটাটা নিচ্ছি ট্রেন করার জন্য যেটা আমরা অ্যানালিটিক নিয়ে করি, তো এই ক্ষেত্রে স্যার ডিফারেন্ট অনেকবার কি ফ্যাব্রিকেট করা দরকার হয়? কারণ প্রত্যেকবার যেহেতু আমরা নিউ জিনিসে
ফ্যাব্রিকেট তো অনেক এক্সপেন্সিভ, রাইট? সো ইটস আ ভেরি এক্সপেন্সিভ প্রসেস. হোয়াট উই ডু ইন জেনারেল, we do it in synthesis level. So I implement the whole GDS to layout, and from there I collected data. Okay, so for a specific technology node, let's say I collected data for 14 nanometer, right? I cannot apply this model for 7 nanometer. So it is for a specific technology node. I have to implement many design, collect data, apply my machine learning, and a new design I want to implement, then I will follow this. So this is the Google work. The left one, as you could see, it is placing its modules. This is the training phase, left one, and the right one is once I train, I want to test it for a new design. So right one is, as you could see, it is showing a very good result. So we have a very clearly there very congestion is limited here, as you could, and we have a clear space in middle where I could put my memories, where I could and enough paths for my routing. So as I said, my motivation is, in general it takes days for RTL to GDS2 generation, and as an engineer you can solve about 200 years evaluation per day. Okay, as an experienced engineer. And in general the existing machine learning models use bias supervised model. So what I did there, and you cannot stop me anytime if you want. What I did there, I had this process, standard process of RTL to GDS2 generation. And as I said, the routing phase is the most hardest and takes days. What I did after global routing, I tried to predict where the problem will be in my layout, where the DRC violation will be. Okay, and it happens how I applied like hundreds of design, I implemented and collected data, and basically after that I found the DRC locations. Okay, so I can correlate my features with my DRC evaluations. As I said, from each grid, basically I collected features, and that grid I can count the number of DRC evaluations also, right? So then I can correlate those features and number of DRC evaluations, right? And basically after that, if I could give a solution before my detailed routing, I am good to go. Because detailed routing will take all the time.
So how about the completion time?
This time is still like we are saving time, because like we do only until global routing. Global routing is probably minutes, right? We'll do that and we'll basically predict, okay, that basically this is the purpose of no human in the loop. So in general, we have a lot of people in the loop in our chip design, right? So what this guy will do, it will implement design, it will go to the global routing phase and tell the designer that the constant you put are not good enough. Change your constant and go back, change your constant and do the logic synthesis again with updated constant. Last year I published a paper on that, a journal article, that I am saying basically what are the constant an engineer can pick automatically.
But how about the comparison? Like you are training the system, right? So how much it takes time for the system to...
Training is done previously, that is offline training. This is nothing to do with real time, right? So we did all the work before. Because it takes days, right? As I said, I spent 1 year on that. So what I did, I applied random forest algorithm, which is a very standard decision tree problem, okay? And basically the random forest, the way it works, it identifies the feature importance. So feature importance like the number of intersect pins between each grid, number of standard cells inside that, number of pins inside that. So all those features we collected from each grid and identify the feature importance to correlate my DRC evaluations. And the results were good enough. So it was published in DAC 2019. Anybody know about DAC? So basically this is the top conference in EDA, okay, in the world actually. So everybody wants to go there every year. And the same year I published one more paper, basically the same idea, but what I did, I applied two ML model and take the weighted sum of their outcome. And this is called soft voting based classification, and the results were a little bit better than my previous one. So ultimately what I wanted to do, basically my DRC evaluations were there in my layout, and I want to predict those DRC evaluations. As you could see, the green and red points are my DRC evaluation and green are my predictions. Okay, as you could see, they overlap. So I was predicting correctly where the DRC evaluation will be happening. And we compared it with our standard SVM model and shows that it is good enough. Now I will move away from this EDA domain, okay? So just giving you a warning that I will talk about a little bit different. So cyber physical system is a system. In general, we have a controller unit, we have sensor system, we have our decision maker, and we have our actuators also there, and the communication unit also, everything together. So in a CPS system, what happened? We are assuming that the system I build, let's say it is a army board, right? A system we build for an army. Now the expectation is anything happen, this board will be always going, it will reach its destination, right? It will never break, right? So how do we assure that? But when we assume that when we start building our cyber physical system, the assumption is all my modules will be always there, right? It will never, all of those will be actively working all the time, and they'll be always on. But what we assumed here is like if something happens, let's say one of my modules lost, computational unit lost, then will it reach the destination or not? Right? So that is the reason we did this work. And this work is basically funded by Office of Naval Research, ONR, and led by one of my colleagues, Professor 𝗏𝗏 And if you guys are interested, you can contact me or Professor 𝗏𝗏 anytime about your future research. Okay, so along this line of cyber physical system. And we have partner of USNA, University of Naval Academy, US Naval Academy, which is at the DC area, and there are like several faculties from there. A commander and a assistant professor also working with us for this project. So the primary motivation is our system will be running and something will happen. Let's say a missile will attack your board and some part of computation is gone. Now what will happen? Can we prepare our system that can tackle these issues? So instead of that, what they do in general, we do basically temporal redundancy. What they do, like we create a checkpoint, right? We are running the system, we create a checkpoint, okay, there, my state is there, okay? If something happens, we go to that state, right? So that is called temporal redundancy. Or we could do hardware resource replication, right? We have one module and we copy this module many times. Now, few modules gone, still we have copies, right? These are called spatial redundancy. Another way is like you schedule intelligently. Like you are very smart and you intelligently schedule in a way that will reach the destination on time. But what we apply here is something very new. New in terms of if something happens real time, we'll dynamically allocate the system or write state and still do the same performance, continue with the same performance. So here I am giving one example of I have two hardware units. They are running two kind of Kalman filter. One is constant velocity model, one is constant turn rate model. Now, if any attack happens, or it could be cyber attack also. If somebody attacked in your system, cyber attack, like you could imagine that any kind of like cyber physical system attack, like any kind of even software attack, right? And then what going to happen? If it is a DOS attack, your system will not respond, right? So what we did, we created a fusion engine and dynamically said that okay, my hardware 2 is gone. Can we allocate this task to this existing hardware dynamically? Okay, on the real time. I'll give you an example and show you a video in the next slide. Hopefully it will work. So this is done by my collaborator at US Naval Academy. Commander, you will listen some voice from Commander and Professor Brian. So as you could see, we are trying to track this board, okay? And the idea is, as long as the board is close to our target proximity, we will apply our best model, okay, CTR. So here we are showing that slot 1 is which model is running. And as soon as the board will go far, this CTR model will go into CB model, constant velocity model, and it is showing here. So as you could see, it went far, and we are applying CB model here. And then it is coming back within our range. Then it is very critical for us. Within our range, we have to be very careful, right? It could be a intruder. Then we have to feed our best model there. So basically, we are constantly dynamically swapping in real time. And then going back. So as soon as it goes outside this boundary, it will go to constant velocity model again. So basically we are tracking it with the radar, TI radar, and that radar data basically we are applying to our FPGA system with the Raspberry Pi controller and constantly dynamically reconfiguring our FPGA for specifically target model. Any question on that? Yes.
আমরা যখন একবার এক এক রেঞ্জে যাচ্ছি তখন কি আমাদের ইয়াগুলো চেঞ্জ হতে যায় না যে ডিভাইসগুলো চেঞ্জ হচ্ছে যখন
Actually my hardware devices are still same, right? But my assumption is I lost one of my FPGA. Okay, but something was running there, right? So I create a checkpoint of my state. That state is stored in my memory, and when I switch back to another module, another hardware, can I start from that? That's what my video was showing. We freeze our model for certain very milliseconds, and then we can get back to our tracking again.
Do you have any data encryption technique there?
Nothing there. Very basic network. The SPI communication is there. Now I'll move to again another research, which is my circuit design, my core research area. Probably it is more relevant to you guys. So I did some work with industry. This is a partnership with Resonant Inc., a Silicon Valley based company. So I did some tape out with them. And initial work was, basic idea was, can we save some energy or power in our computation from our microprocessor? So in general, the way we consume power in a microprocessor is 0 to 1 transition, right? So what happened when there is a 0 to 1 transition, we store some energy at our output, okay? That is giving us one output, high output. And 1 to 0 transition, basically we dump our energy into the ground. So this is the process in general. Each computation we consume about CL VDD square of energy. CL is my total load of my capacitance of my system. So what resonance does basically is connects the inductor and resonate between a inducting magnetic field and electric field of my capacitor. So basically the energy will resonate and store some energy. Instead of dumping at 1 to 0 transistor, it will store some energy to the inductive field and resonate back. So what I did with that company is like we applied this thing in cache memory design. I don't know, anybody know anything about cache memory? So basically this is the closest memory system in my processor, where basically I go, for each time of computation, I go to my cache, grab my data, compute, and go back, store my data again to my cache. So this is the closest and smallest memory system in our computing system or processor. Every processor has that. Your mobile devices, your laptops, desktop, everything has. So this kind of cache, in general, the 66 transistors cell-based SRAMs. So what I did there is basically from my bit lines, I connected a switch, and those bit lines are connected within a common inductor. Okay? So when the bit line discharges, I store some energy in the bit line inductor, and when I need to charge it or write my data into my memory, I can utilize this energy, stored energy. And this curve is showing you that what the resonance was. Like as you could see, this is my free resonance up to this point, and from there basically I have to connect external battery to pull this load to my full output swing. We designed 144 kilobytes of SRAM cache with a K2 processor, and we could save in our cache about 50 to 20% of dynamic power. And as I said, the K2 split processor we developed and taped out using 28 nanometer TSMC technology, and overall the saving was about 20 to 30% of processor power in cache plus the clock network. We applied resonance in two phases or two systems. Now again I am jumping into another research. So basically I am giving you, yes.
Sir, in this method, so you were attaching as a single inductor to the processor?
Not necessarily. In general it is distributed. But for cache it is very simple, right? So in the cache all the cells are together, right? So I can create a switch in between bit lines and then connect it to the, if it is big chunk of capacitance, it is easier. So I can connect one inductor. But for clock network it is difficult. Clock is distributed, right? All over my processor. So on that case we connect distributed L. For that we have algorithm also. I spent about 10 years in clock routing. So I spent all my life there. So I have dedicated tool also for clock routing.
Sir, yes.
Cache that on chip, because it is my close. Outside with the DRAM, right? So we could have DRAM for that, or we could have flash. But this is closest to my processor, so I have to build on chip, close to my processor. Otherwise, you will spend all your time to bring data, right? So you don't have that for cache. So I am jumping into another research, neuromorphic computing. I am doing this research last few years. Not many publications because I am writing proposals. So I will not reveal most of my work, you can say, but I will talk about basic motivation of it in general. we assume that the brain computation is very energy efficient compared to our accelerator, the microprocessor we develop in industry. Even the billion-dollar processor, the brain is much more better in terms of energy efficiency. The comparison is 20 watt versus 3.6 megawatt for accelerator design. How it works, our sensory system, as you could see, our sensory system will sense the real analog data, right? So what it's going to do, it will go through a sensory transduction neurons and it will create a spike depending on my input data, right? So there will be spike encoding. After that spike, basically it will go to my neuron, and depending on the rate of spikes and the frequency of those, my membrane potential will go certain level, and if it reaches certain level, the neuron will fire. So this is the biological way of neural network. Now for this, what I did, I built a tool where I train my model using regular TensorFlow. I could build a artificial neural network or a convolutional neural network, and then I check my accuracy for my benchmarking purpose, and then it goes to ANN to SNN conversion. So I mapped this artificial neural network one-to-one as a spiking neural network. And as you could see, after my training, I check my accuracy. After my conversion, I will check again my accuracy, and I try to see how much loss is there. Okay. And the primary motivation is, our assumption is spiking neural network is much more energy efficient than my regular ANN. Then after that, we have this spiking neural network. Now I have to fit this large spiking neural network in my hardware, right? So I am assuming this as two problems. One is graph partitioning. So I have this large neural network. I have to partition this neural network so I can place those neurons into my hardware. Okay, so this is the graph partitioning problem. Then the placement problem. So I have to place those clusters into my real hardware, right? So then I am saying that this is a NOC problem, network on chip problem, and finally I build my SNN on my hardware. So I give a very tiny example here. So this is my initial spiking neural network. Then I said, okay, after partitioning, this looks very organized on my chip, and these are my grid nodes of my NOC, network on chip. And finally it shows the heat map. And then I did this is the tool I did. Basically my undergraduate student did that. And I published a paper in a couple of days. I'll give a talk at AEEE. There will be a conference where this work is published. And two of my undergraduate students, they did this work. It was summer 2021. Very smart. They helped me a lot on this implementation. Two of my undergraduate students. And these are the benchmarks. So I implemented different kind of neural networks and converted into spiking neural network, and shows that how much accuracy we lost from my ANN to SNN. And as you could see, the error was about 2.65%, which is in general manageable. So the reason for these slides is basically I am saying that I am doing work that is inspired from nature, that is inspired from our brain. In addition, I am doing some work that will be connected the brain decision making with my internal organs. Okay, so that is in general, in scientific language, we said introspection. Okay, so I am doing some work. As I said, I am not presenting my core research. Last 1 year I am doing in this domain because I am submitting proposal with those. Okay, but think about that. The internal organs also contributing our brain to make decisions, right? So think about a food you want to eat. A food is there, it looks good, you want to eat, you like this food, but if your smelling system said this is rotten, right, your decision will change, right? So that is, I say, this is kind of decision making or internal organ that modulate our decision making or brain decision making is introspection. So I am trying to connect this decision making, our neural network decision making, with our internal organs signaling system. Okay?
Same question.
Yes.
So, using this introspection technique, is it possible to detect or predict diseases? Like,
this is very hard. Like in general, introspection is your internal body, right? So let's say like the way we set up the experiments or the literature set is like, let's say somebody is sitting there experimenting human, and you ask to do, okay, whenever you feel that your heart is beating, you click, right? So you click that. Now how do you correlate that, right? So there is a real system sitting there that will also detect that your decision or your assumption that heart was beats is also true or not, right? So interoception is something mathematically it is very hard to define. So scientists are still trying to come up with some models. So I proposed a model recently. It is recorded, but I don't know whether I should say. I submitted a proposal. It was rejected. Like yesterday, I got the news. $2 million proposal, but actually nobody understands what I said there. Bottom line is that. So I built a model for this kind of architecture, but I could not explain enough. Bottom line is, if somebody rejects you, it means I was not good enough to explain them well, right? So it was my fault. So it is not their fault, not reviewers' fault. It is my fault that I could not explain more. But I'm trying myself, every day I'm trying to improve myself. Okay? End of the day, I ask myself, every day, did I learn anything new? If not, it was waste of my time. Because my life is very short, right? So if I lost one day and didn't learn anything, that is waste for me. Every day, even now. And if you come to USA, I will challenge you that you cannot work more harder than me. Okay? So you see me how I am working there every day, 15, 16 hours in my lab or my office. Okay? Every day. So I will switch to another research again. These are all funded research. As I said, this one is funded by Maryland State with a company I am working for. That is called 𝗔𝗂𝘀𝗘. So they build basically image sensor. But what my team is doing, we are trying to, they are basically an event camera based system. So they are capturing events or videos. What I am building an AI platform that will say, okay, this image is saying something. This image is a human. Or this image is like somebody driving. Or a pet, right? So my model has to be small enough to integrate with their imagery. Okay? So I am helping this company 𝗔𝗂𝘀 to build this. So here I am showing one unpublished work, but the basic idea is like I have this hierarchy of processors where depending on my activity of my system, if let's say my surveillance camera is there, right? If there is no activity, do I need my fastest processor to run there? I don't need that, right? If there is an activity, then I will run my fastest processor and waste my battery, right? So this is the idea here. So depending on my activity of my image, I will trigger my different layers of accelerator, initially it will be very small, a classifier that said, okay, some activities are there or not. And then it will go to next stage of network that will basically set that it's a face with that much of confidence. Then I will trigger my main full frame processor where I will say this is a human face, okay? Or like specifically that classifier will say something. So the idea is like we'll have these videos captured from each frame, or like I will take different frame difference and set that okay, some activities are there. It's binary imaging, right? If there is an activity, I will create this binary image, and from there basically I will apply different kind of architectures to find out what is in this image. Is it a human or like depending on my application, right? So that company has like currently they are trying to detect faces. So what I did there, we built some novel architectures and put it on Raspberry Pi model, embedded processor to benchmark. And the interesting part was like inference time was about 2 orders of magnitude reduced. Any question up to this point? So I will switch to my another research. I am giving you some idea of what I am doing last few years. If you guys are interested, you can always email me for more information. I can give you papers. If you are interested to join our group there, you are more than welcome to come and work with us. And even remotely, if you are interested, a lot of students are working remotely with us. One university from Pakistan, there is a group working with me, and India also. And I am trying to build something with Professor Hassan to see if there is a group they are interested on hardware software code design. and we could do some new work. As I said, I will go to my another research domain, which is funded by National Science Foundation and Maryland State, vehicular network security. Though it is not for VLSI, but in a way the VLSI designers, we trained ourselves in a way that I can solve any problem. Okay, you give me a problem, my training is I will come up with an idea and implement that. That is the reason I could switch different areas of my research. So vehicular network, I'll give you briefly how our vehicles connected. So vehicle ECUs, electronic control units, they are connected in a network. In general, we call them control area network, CAN network. Okay. So there are multiple networks there, CAN especially, to control our engine, control our other infotainment system. But all those ECUs, electronic control units, has their own connection with my control CAN network. Okay, everybody is talking to my CAN. The problem with CAN is like this kind of network is visible to everybody. You connect a device in your OBD2 port of your car, and you can see all the CAN messages. It is visible to everybody. Though the messages you cannot encrypt. Those are encrypted data. You cannot decrypt, but you can see those messages. So that is the reason this is not very secure. Some sort of different kind of attacks, already established attack, we have seen fabrication attack, which is basically nothing but like I am an intruder, I will act as a real issue and start sending message to my CAN network. Another kind of is DOS attack or suspension attack, that is like basically stop one of the issue. That issue cannot send any message. Another is like masquerade attack, which is like I will stop an issue and I will start sending message using the same ID. So I basically act, let's say I will act as a Professor Ayasan and start teaching you guys, right? So that is that kind of masquerade. So this kind of attacks are already established. Now, what are the way we characterize our issues? So there is a standard way. I believe everybody is some sort of familiar with clocking system. Like let's say I have a processor, it has a master clock, right? So that clock is nothing but my oscillator, right? And it has a unique characteristics because it's a on-chip oscillator, right? So if I track my clock, I'll say that each time it is giving me a frequency, if there is a delay in between, I can measure that. For each issue in my car system also, I can measure that error, frequency error, for specifically one issue, okay? Because it is running with one clock, right? For each issue there will be a clock, and basically this is saying that error of those clock offset, okay? So which called accumulated offset. So basically you can characterize or fingerprint your issues. So I published a paper in 2020 on this. Basically I am saying that can we dynamically allocate those IDs? Okay, so each issue send message with a specific ID. So that was one of the published work. And then one more unique idea I give in this domain, I can brag about it. This is the first time somebody sees a CAN communication as a graph problem. Okay, and I filed a patent on this year. Actually not this year, this is not 2022 right anymore. So 2022 I filed a patent, US patent on this. So what I am saying, this is the CAN message. Can we build graph out of it? Once I build my data structure graph, I can say that this is an anomaly detection problem. Okay? So it was published a TITS, like a very prestigious IEEE journal, this idea, and I used a very basic model, statistical model. So what I did, I applied chi-square model, which is more than 100 years old. So mathematically, in general, like I say, like last 100 years, we are not advanced enough. So we are applying all those mathematical models established 100 years back. So there is no new mathematics. So I applied chi-square method, which is a very 1913 published work. So what I did, like for let's say a CAN network is running the car, and I can extract all those CAN messages and do a statistical analysis to create a base hypothesis without any attack. Then once I have this base hypothesis, I can compare when it is attacked, how much statistically my graph changes. right? So as you could see, you can clearly detect those changes, and from there I can create my threshold and say that whether it is attacked or not. And the results are very interesting, and first time basically I showed that it is possible to detect combined attack with a single algorithm. Then last year also I did some work on this, considering the Google page rank algorithm, where the website, each website will be ranked depending on the number of nodes coming. Or this is a very standard algorithm Google uses. And from there, basically, we extracted features, and from there we applied the Bayes theory, very basic Bayes theory for continuous variables, collecting features from my graph, applying Bayes theory, and then basically likelihood computation we did and compared that like the attack versus non-attack nodes. There is some work on the graph feature importance, correlating my anomalies. And what we do when we detect anomalies, basically this idea is presented here. So I have my car, I'll extract my CAN messages, and I'll build my data structure, graphs, and from there I could extract my features and apply anomaly detection. After attack is detected, we can say to take action by the driver or my server processor. How often we do this? So that's why I did some sensitivity analysis. We have our prototype built, where I built the CAN network with the RC card.
Sir,
Yes,
can I ask a question from the previous slide?
sure.
So এখানে বলা হচ্ছে sensitivity to window size. Window size বলতে কি per window তে কতটা ডেটা রাখা হচ্ছে সেটার উপরে sensitivity.
Window means here, like think about like how often I am building my graph, right? So the CAN messages are going right with certain speed. Let's say 1 megabit per second. Now, if I said like 10 millisecond, within 10 millisecond, I will build a graph, or 200 millisecond, right? So that is user defined. Okay. So depending on my CAN speed.
That means window size যদি আমার বড় হয় তাহলে হচ্ছে স্বাভাবিক আমার
গ্রাফ সাইজটা বড় হয়,
সাইজটা বড় হয় anomaly ডিটেক্ট হওয়ার চান্সটাও বেশি
বেশি।
ওইখান থেকে sensitivity তাহলে কি
Just sensitivity is saying that window size will not change your detection and capacity. Okay, for certain data set. So we applied on certain data set. So this is the prototype I built in my lab with Arduino board, very basic RC card, Arduino board, and build a CAN communication network and connect some sensors like imager and some sort of ultrasonic sensors, and then we tried to show that how we can detect our attack. Any question? And this is what I implemented on my FPGA. So we used ping Xilinx ping board and showed that the accuracy of my attack detection was about more than 96%. And interestingly, the inference time was like in the order of like, as you could see, probably in microseconds. Yes.
From the previous video you just showed us, এখানে অ্যাটাক যখন হচ্ছে ঠিক এক্স্যাক্টলি কোন পয়েন্টে অ্যাটাক হচ্ছে এটা
It depends on us, right? So it is a toy example, right? So we built our model and showed that how often we can create those attacks and how much. And basic idea is how long it takes to detect my attack. So inference time is important, right?
এটা তো লাইন ফলোয়ার রোবট দিয়ে করা হচ্ছে।
Line follower is just a toy example, right? Here I am saying that we build this prototype. Now here I can connect sensors and a CAN communication, right? So after that CAN communication, can I introduce attack there and say that my computational module inside this, right? If I connect an FPGA, how fast it will detect? That's what we wanted to show here.
In this video, did you show any attack?
No, this was just a prototype. This is like FPGA results. As I said, the inference time was 0.076 milliseconds, and these are all my sponsors, almost all the federal agencies and the state. Some companies are funding my lab, and I want to talk about little bit about my department. My department is more than 30 tenure track faculties, more than 50 professor in practice, lecturers, industry lecturers. It's a very large department. We have 3 PhD program, PhD in electrical engineering, PhD in computer engineering, PhD in computer science. So if you guys are interested, I am basically looking at computer engineering side. If you want to work with me, or there are several other faculties I can talk about. Several faculties in computer science, very renowned in their domain worldwide. Professor 𝗏𝗏𝗀, Professor 𝗔𝗵𝗏, Professor 𝗔𝗵𝗏𝗀. They are very renowned and they are doing great work with government and different organizations, different industries. And me working with Professor 𝗏𝗏𝗀, and we are very hardworking, I can tell you, and we are funded by almost all the federal agencies. And I am also working with Dr. Justin Brooks. He's a doctor by profession, MD, PhD. And Professor Nilanjan Banerjee, he's in the computer science side. And we have several other computer engineering professors. Professor Tinush Mohsini, she's our graduate program director. She's doing great. Career award she got. Professor 𝗏𝗏𝗀𝗏𝗏, she's also career award recipient. She's doing hardware security. I am also doing a lot of hardware security, I can tell you. I didn't show those slides. The idea is like I implement RISC-V processor on an FPGA, and then I can track different kind of instruction running there using my EM, electromagnetic probes. So I have a setup in my lab where I am tracking different kind of instruction even using my probe, not even connecting anything with my chip. Okay? So side channel attacks, those kind of hardware security attack, the work is going on in my lab. And as I said, my lab is funded by all those organizations, and I must say all the work is done by my graduate and undergraduate students. So I am thankful with their work and support. If you have any question about my department, if you are interested to do one of those work I showed, I'll be very glad to hire you guys. And basically I want to work with people who are hardworking and committed, and they want to create their own name, right? Not depend on other people or the university name. And in the USA, I can tell you one thing: if you are good, people will come to you. It doesn't matter which religion you follow, what color, what tone you talk, they'll give you value. So USA is open for everybody. Okay? Thank you so much. It was a small grant they give for specifically radiation hardened technique. So I didn't show those slides probably. Here. So when radiation affects the cosmic radiation, our electronics memory changes, flips. So that's why like anything going above sea level, the data could flip. So we build system or circuits that is radiation hardened, specifically memory, cache memory. So I did some work on this film.
So, thanks to Dr. Islam. If you have any questions,
I'll be very glad to work with you guys. Okay, I'm just very clear about it. If you are hardworking and committed, that you want to create your own name, you want to have your company in USA, you can work with me. Okay, I'll help you.
So I have two questions.
Yes.
The first one is what type of VLSI design work you do in your labs, and what kinds of opportunities?
Currently, we are fabricating a RISC-V processor. It's the DoD funded project, and Professor 𝗏𝗏𝗀𝗏𝗏 is leading that. I am part of it. So we have our initial tape out on 45 nanometer. I didn't show any work on that, so currently one graduate student is working on it. We are going for next phase of tape out. Basically, we are trying to show that with RISC-V, can we create a root of trust there? Like any, because like these are for mainly for the security purpose. How much security you could put on our RISC-V. So this is one kind of VLSI, but as you could see, like I am doing a lot of other work. They are always connected with VLSI, because anything I am doing, even IDS system, I have to implement on hardware. Yes. So that part is done by VLSI, right?
Do you do the layout designing also in your lab?
Yes, tape out you have to do the layout, right? So, but we do a scripted, like we script the whole thing in like thousands of lines of tickle script, and I use like those synthesis tools. But we do custom layout also. Basically, I showed like some work I am doing with Resonate, one company, they are funding me, so I do circuit design for them and the EDA.
Thank you so much. And the second question is, in the slides you showed about cyber physical system outside the computer. So I was just wondering if this kind of system can be also implemented for, let's say, space industry. Like there is also a lot of reliability problems.
Yeah, of course. The ARL is also working on this CPS system.
I have a question about the spiking neuron. So, it's a nice question. For neuromorphic computing, so people sometimes they focus on designing synapses that are biological like synapses. Like, what will be your synapses? Those you gonna use in the hardware?
Finally, the target will be going to the hardware. At this point, we are still in the high-level side. We are building spiking neural network. We are collecting weights, and basically spike rate and how frequently they generate, and we implement those on embedded system on hardware and map it to a NOC model. So it is very high level now, but we are showing the feasibility of it in high level. But if you want to design your circuit, you can design your own neuron and apply the hierarchical model you have and build your own spiking neural network. It is possible. What
Can you make that possible, designing the whole hardware? Then can we call it like an artificial brain?
Of course, it is called artificial brain, but how close it will be because of that interconnection we have is very difficult. But the brain is like, you can say 3D connections are there. But our technology is not good enough to have 3D models still because of the heat issues, right? So we cannot do stack, too much stack. That's why like the industry cannot go up to 3D model. But once we resolve the interconnect problem, probably it will go more closer to this 20-watt barrier. Anybody interested to work in research domain, definitely like you are welcome to talk with me or Professor Oguchi for future references, anything you need. Just shoot me an email and that we can go from there.
Do you guys have any more questions? Okay, if not, then let's thank our speaker one more time.
I request you. সব পার্টিসিপেন্টস একটু সামনে চলে আসি